Okay, so let's look at redox reactions from the very beginning. Okay, to start off with, what is a redox reaction? Right? So the red ox stands for reduction. So that's the red bit, reduction.
Yeah.
And then
Yeah.
let's actually do a different color. So let's do the reduction and say red. Because then we can just think reduction, red. So reduction. And then your oxidation, let's do that in blue. So that'll be oxidation.
Sorry, give me a second.
Okay. I'm just going to switch to my mobile hotspot quickly because I see my internet's unstable.
Yeah. Hello? All good.
Okay.
Tell me good.
So the first thing is the red, reduction and oxidation. So there's a couple of things that we have to remember. The main one is that this deals with oxidation and reduction deal with loss or gain of electrons. So we know that whenever we have these reactions, electrons are the thing that move, right? So our protons and our neutrons stay in the middle of the atom, but our electrons can be transferred. So it's basically the loss or the gain of electrons. That's what happens in a redox reaction. One thing gains electrons and the other thing loses electrons. And so we have to remember the line oil rig, oil rig, oil rig. Okay, so I've done the red in the R, the rig part in red, because reduction is gain. That's what the rig bit stands for. The reduction is gain. So the substance that's being reduced gains electrons. So it's gain of electrons. Okay.
Yeah.
And then the oil is oxidation. So oxidation is loss. So that's a redox reaction. And that's what will happen. So let's look at an example. So we could have something like zinc, Zn plus Cu.
Yeah.
Now that could go to copper plus ZnSO4. Now you can see the SO4, but that's just the kind of spectator ion. That's there. It's going along for the ride. But what we're really looking at is the Zn, the Cu, and what's happening to each of them. Okay, so
yeah,
this will often be written as, instead of Zn plus CuSO4, it might be written as Zn plus copper. Now, SO4 is an ion that's 2 minus. So in this situation, the copper is 2 plus. That's what it has to be for it to balance. And so then it goes to copper plus, and now the Zn is now 2 plus.
Yeah.
And so So that's a fairly common one. So let's look at what's happening with the Zn. So the Zn2 plus. So it's going to Zn2 plus. So for this to go to positive, it must lose electrons. So if I was to look at what's happening with the Zn in this redox reaction, deciding what's losing and what's gaining, the Zn is going from, now this is called a half reaction, what I'm going to do. Let's look at what happens with the Zn. So the Zn plus 2 electrons goes to Zn2 plus.
Yeah.
Sorry, it will go here, not plus 2 electrons. We'll go to Zn2 plus 2 electrons. Because it must have lost electrons to get to positive. So what's happened here? It's lost electrons, right? Because it became 2 plus. So would this be oxidation or reduction?
Oxidation or reduction?
Yeah.
Wouldn't it be oxidation?
Because oxidation is loss. I'm just going to write more space. Oxidation. Because it's lost electrons. So the Zn has got onto Zn2 plus 2 electrons. Let's look at what happens with the Cu2 plus. So the Cu2 plus, it's positive. So how does it get to Cu? Well, it must gain 2 electrons, right? Because it's 2 plus over there. How does it go to neutral? Well, it must gain electrons. And so this must be the reduction half reaction. Okay. So this is a redox reaction. The zinc has gone to Zn2 plus 2 electrons. And the copper 2 plus has gone to copper. And so it gained electrons.
Yeah.
So if something goes from 2 plus to neutral, we think of it as neutral, it must have gained 2 electrons because electrons are the negative bit.
That's Cu4 plus.
No, because it's gone to just Cu. Because 2 plus 2 minuses gives you nothing. So if I highlight this and this, we're looking at 2 plus 2 minuses because electrons are negative.
Yeah.
Plus 2 plus minus 2, because that's 2 electrons, equals 0. So that's how we get there. It's a little confusing.
Yeah.
We just got to keep it in mind and do a few practice examples. So redox is a reaction where the electrons are transferred from one substance to another.
Yeah.
So in this situation, we knew exactly what was reduced and what was gained. But let's say we didn't know. Well, this is where we get to our half reaction table. Let me just clear everything. So this is a past paper. Now you'll get given a sheet probably separate from this. But this is what the half reaction table looks like. Okay, so it's a table of standard half reactions.
Yeah.
Now, the top one is fluorine. Now, if I go to, okay, so let's just take note of the top one, fluorine, which is F2 plus 2 electrons goes to 2F minus. So what's happened? Has it gained or lost electrons? The F2, has it lost or gained?
It has gained electrons, right?
Good. It's become minus. Excellent. Excellent. So I'm just switching to mobile.
Wouldn't it have gained? Yeah.
It's
So it's
gained
throwing more
electrons.
electronegative.
It's gained electrons. It's become more negative. There may be a slight delay as I switch to mobile data. This Wi-Fi seems to be unstable.
Hello? Oh, okay.
Okay, so we were doing our oil rig, right? Reduction is gain. So the red was the reduction rig. So this is a reduction reaction. This is reduction because we gained electrons. F2 has gained electrons. F2 gained electrons to become 2F minus. So of course there would be ions involved in this, which would be so that F probably wouldn't be alone. It would be sort of on like might be F2SO4 or something like that. We're just writing this sort of half reaction because the F is the thing that gains the electrons.
Yeah.
Now, this table tells us exactly when you have two things reacting, which will gain and which will lose. And the trick is to learn whatever happens to fluorine, that then governs the rest. Because if fluorine is always reduced, then whatever's highest in the table or closest to fluorine will be the thing that is reduced. In other words, will be the thing that gains electrons. So if you have two things that you're given, like say you're given chlorine and bromine, you compare them and you go, well, chlorine's closer to fluorine, and we know fluorine is always reduced. Therefore, the chlorine will be be reduced in this whatever reaction we're looking at. In this reaction with say Br2.
Yeah.
Okay, it's a little bit tricky, but what I want to do is say you forget what's happening. I want us to look at fluorine, where it is in the periodic table. What is the fluorine's electronegativity? It's 4.
Yeah.
So we remember that fluorine is the most electronegative element. If we look at it, it's got the highest number, the 4.
Yeah.
And we know this electronegativity means how much something is hungry for electrons. It really wants electrons. Fluorine is dying for an electron. Because if we look at fluorine, what it looks like, here's fluorine here. First of all, it's very high up, which means its valence electrons are really close to the atom, the protons, the nucleus, I mean. And we know that fluorine group 7 has 7 valence electrons because it's over here.
Yeah.
And we also know the octet rule means that these atoms, unless it's hydrogen that has 2 or helium that has 2, the others all have this 8. And so it really wants to get 1 electron here, because then it can be complete and it can be sort of like neon, right? We know that atoms aspire to be noble. They want to get that noble configuration, that neon. So fluorine, rather than lose 7 and become like helium, would rather gain an electron and become like neon.
Yeah.
So this is why fluorine is so electronegative, because of it. First of all, it's high up the table, meaning that it's got the two inner electrons, but then the outer orbital, there's only one outer orbital, because as we go down, right, this is one orbital, 2, 3, 4. So
Yeah.
being in group and in row 2, it's really close to the center, those valence electrons. And so the positive nucleus is sucking them in. So the main takeaway from that is that fluorine, being so electronegative, is always reduced. So as long as we remember that, we can figure out what's happening in this table.
Yeah.
So that allows us to check what's going to happen with our reaction. So if we look at fluorine, it's at the top. So fluorine is always going to be reduced. And then if we go down to the bottom, we have lithium. So lithium is always going to be oxidized. Makes sense, because if the top's reduced, then lithium must be oxidized. And let's have a look at where lithium is. I'm going to move it down slightly so we can see lithium. So lithium, look, it's right there.
Yeah.
And lithium has, how many valence electrons does lithium have over there in group 1? Over here. Group 1, how many valence electrons? Are you there?
Yep. It's 1.
Excellent. Good. So I didn't hear you. You might have had your mic off. Okay, 1. Perfect. So that makes sense, because helium is noble, so that has the complete 2 electrons in its innermost orbital. And then, so it has that, complete inner orbital, the 2 electrons. And then lithium has 1 on the outside. And we know the outside octet rule has space for 7.
Yeah.
I'm drawing it a bit differently just to mix it up a bit. So it's going to really want to lose that 1 electron and become like helium, rather than trying to gain 7. It has to try and gain 7 in order to become noble like neon. Much easier for it to lose 1 and become like helium. So it's always going to lose. And we know from our rhyme, or that word, OIL RIG, oxidation is loss of electrons, oil. So the lithium is always going to be oxidized. So that was blue.
Yeah.
Okay, so on the other side, we had lithium. So lithium plus, that's going to want to lose an electron. So it becomes like that, right?
Yeah.
So it goes the other way around.
So go from Ally to Ally plus.
Yes. Yes, correct. Should actually do it like this. Plus an electron. So lithium has lost this electron. As you said, it's going from
Yep.
Li to Li plus. Good.
Yep.
Okay, so then we now know how this half reaction table works. We now know that if we get told, two things react, and what's going to be the oxidizing and what's going to be the reducing agent. So we remember the oil rig, oxidation is lost, reduction is gained. Now the next bit we have to remember is that the thing that gets oxidized is the reducing agent. Have you been taught that yet? So if I'm oxidized, that means I'm reducing the other thing, because the other thing is being reduced.
Yeah.
So the oxidizing agent is reduced. And that's where a lot of confusion gets in. So don't get confused. So the oxidizing agent is reduced, and the reducing agent is oxidized. So if the fluorine is getting reduced, it is the oxidizing agent. Okay. And the lithium, we said, was oxidized, which means it is the reducing agent.
Yeah.
It's the reducing agent. So just the main thing there is to remember that get rid of these. Okay, so now we know what a redox reaction. It's a reaction that takes place between a reducing agent and an oxidizing agent, where one of these atoms or molecules is reduced and the other one is oxidized. And we can tell which one because we just go to our periodic, go to our half reaction table, and we can see.
Yeah.
So these are very handy in cells. So the next thing you have to know about the table, so you know how this table works now. It's basically telling you which is the oxidizing and which is the reducing agent. The next thing we have to know is that they have a potential difference, and that's what happens in a cell. So you can imagine that if you put two of these chemicals in a cell,
Yeah.
and you know that when you put them in a cell, the electrons will move from one thing to the other. That's a flow of electrons, which essentially is a voltage. It's a current. So you can create a cell by putting these two chemicals in a container or whatever you want to put them in. And they know now how much potential each of these elements has. And that is this column over here. Okay, so if we know when we hear about batteries and we hear about Tesla, we hear about these lithium ion batteries. Okay, you don't really have to know this, but one of the things about the lithium ion batteries is that it can kind of keep going on for basically almost forever. Like,
Yeah.
I mean, they've made them that they almost lose nothing. One of the issues was that in these cells the reaction would sort of run its course, so it would have so many life cycles before eventually it kind of just died. The battery died. But we also see that lithium over here at the bottom has this minus 3.05, this huge potential. It doesn't really matter if it's negative or positive. That's just relative to, they use hydrogen in the middle, just like they use the atomic weight of hydrogen. Like hydrogen has a molecular mass of 1. they kind of just also use the half reaction of hydrogen to two hydrogen ions and 2 electrons. They kind of use that as a standard of 0, and then everything is just compared to that. So lithium being right at the bottom, very easily reduced. So it's great in batteries because it really wants to gain electrons. So if you have lithium somewhere, it's going to try and it's hungry for those electrons. So as long as you kind of keep, once it gets them, you keep taking them away, it's going to keep wanting to get them. And so gets it, takes it away, gets it, takes it away. Now you have a flow of electrons. And this is essentially what you need to power cars or whatever it is. Okay, so that's kind of the basic introduction. We can now, I think we can end it there. Because we can then, in the next one, we can go on to the next thing, which is REDCat, which is reduction takes place at the cathode and oxidation at the anode, which is how these kind of batteries or cells operate. You have a positive and a negative, and so electrons can flow. Okay.
Yeah.
Any questions about redox reactions? Do you know what they are now?
Yeah.
Okay, cool. I'm going to end it there, and then can you send me a link to a meeting from your side? Would you be able to email me one?
Yeah, I'll send you one.
Perfect.